All right, so timely question on switches for the homework and labs and such. So, bless you. So there's a symbol for a switch, right? This is going to whatever circuit, whatever input you need on the circuit. So the way you want to wire a switch is take this part that's going to the input, run it through a 1K resistor up to 5 volts VCC, and take the side that can get connected optionally through the switch and connect that to ground. That's your symbol for ground, or you can label it GND. And now this point will be at 5 volts, logic 1 normally with the switch open. If you close the switch, this will get pulled down to ground. So another option in that homework, if you drew your circuit for part E, I think it was, without inputs, you could take an input from that and label it A, for example, and then down here just put an arrow and just say it goes to input A, right? And put a note somewhere saying, you know, connects to circuit in whatever that part was. I think it was part E. And this is also what you do if your schematic is too big to fit on one page. You can make these connection points. And a lot of times these things are, you know, letters with circles around them to tell you that they're going to be referenced on another page as opposed to just a label. And then when you're putting these pages together, you just sort of know that goes to that. I have the blueprints for a 1980s era computer that was, you know, about this tall and about twice that wide. And I made a copy of the blueprints. They're sitting in a storage bin in Virginia. I should really bring them out for this class because they're like so cool to look at. And it's just using the same kind of chips that we use in our parts box. It's just these 74 family chips and gates and 74 181 for part of an adder and all that kind of stuff.
How much of the computer is actually switches and AND gates? How much of it is like power or cooling?
So for the computer I'm thinking of, it was just rack after rack after rack of these circuit boards, right? And each board would be, you know, maybe about 18 inches by 18 inches and basically covered with chips. So like if you open your parts bin and there's a piece of foam rubber with chips in it, it's kind of what it looked like, right? Just totally packed with chips, and there might have been a few dozen of these boards in there. But then a lot of it was power supply, and a lot of it was open space so that he had a place to go as the fans blew and so on. So, an interesting mix. All right, let's look at truth tables. So we already saw an example of a compressed truth table. But let me do this more generally. So let's suppose we have a truth table with 3 inputs, A, B, and C. And some output F. And semi-random values for the output F. So 3 inputs, 8 rows in the truth table, 2 to the third. So we're going to do what's called compress this truth table. And we compress around a variable. It means we're basically going to move that variable out of the input column. When we have fewer inputs, we have a smaller table. So let's compress this truth table around C. So I want a new truth table which only has A and B for inputs. But I'm going to allow C, or some equation involving C, to appear in the output. So suppose A is 0 and B is 0. What can I say about the value of F, just looking at this original truth table? It could be 0. Could it be anything else? If it has to be 0. If A is 0 and B is 0, F has got to be 0, because C is either 0 or 1, and in either case, F is still a 0. So there's absolutely nothing wrong with filling in a 0 right here. All that's saying, if A is 0 and B is 0, F is guaranteed to be 0. And yeah, that's absolutely true. Okay, what if A is 1 and B is 0? So this third row, what can I say about F?
It's a 1.
It's got to be equal to 1. It's either a 1 because C is 0, or it's a 1 because C is 1. So this is going to be a 1. All right. Trickier, what about this fourth row? A and B are both 1. What can I say about F? Yeah, it could be a 0 or a 1. How do I know what it is? Is it going to be a 0 or a 1? Well, it turns out that if C is a 0, F is a 0. If C is a 1, F is a 1. Right? Just looking at this case where A and B are both 1, F is always the same as C. So here, I'm just going to write down a C. All right, what about the second row? A is a 0, B is a 1. What does F look like? Looks like C bar. So there's a smaller truth table. It only has 4 rows, only 2 input variables. But my output function is more than just a 0 or a 1. It might have inputs, it might have complements of inputs. But that's what we mean by a compressed truth table, in this case compressed around C. So we got rid of C. Yeah?
You mostly do this just to make it easier to read?
It might be to make it easier to read. It might be because you want to do a K-map and you've got 5 variables. But if you compress around one of them, now you got 4 variables, you can do a regular 4x4 K-map.
But I mean, wouldn't you just convert C bar or C to a 0 or 1, whatever you...
Yeah. But we can actually make a K-map where instead of having just 0s or 1s, we have C bar or C in some of the boxes. And there's a way to redo K-maps, what's called a compressed K-map, based on a compressed truth table. Can we compress this again? Let's compress this around B. I haven't tried this. I always get to this part and I think about doing this and we're out of time. We got time. Let's compress this truth table around B. So if we're going to have an input A and we're going to have an output F. And A is either 0 or 1. So if A is 0, if A is 0, F could either be 0 or it could be C bar. And it really depends on the value of B. So if B is 0, F is going to be 0. If B is 1, F should be C bar. So if B is 1, F is going to be the value of C bar. And if B is 0, 0 ANDed with C bar is going to be 0, F will be 0. So we can rewrite these first 2 rows with this B and C bar. I'm not going to ask you to do this on a test. We're just playing. Suppose that A is equal to 1. So now we're just looking at these 2 rows. F could be either a 1 or a C. Well, if B is a 0, then F should be a 1. If B is a 1, F should be a C. Sorry, that should be a BC. So that's a super compressed truth table. And we got two variables and some weird logic in the output. What's going to happen if we compress this around A?
Are you just going to have an output?
You're just going to have an output. And guess what? It's going to be an expression for F in terms of A, B, and C, which is sort of the most trivial truth table of all. It's not really a truth table at all. It just says F is equal to blah. Okay, so that's the basic idea of compression. What I will ask you to do on test is compress around one variable. So take something like this and turn it into something like that. I won't ask you to compress a second time.
What we did to compress it.
To go from here to here?
Yeah.
So let's make a different variable G. So to do this compression, since we're compressing around C, we need to have this ordered with C last. We start with this first pair of inputs. A is 0 and B is 0, right? So it's these two rows that we're looking at. And whatever we put here should be the value of G in these two rows. Well, pretty clearly the value of G is exactly 1. Right, it's 1 here, it's 1 here. It doesn't really matter what the value of C is. If A is 0 and B is 0, the output's guaranteed to be 1. So this one's not too tricky. But the second one, A is 0 and B is 1, the output could be a 1 or it could be a 0. So we can't just write a 1 because if C happens to be 1, the output should be 0. And we can't just write a 0 because sometimes the output's 1. But if we write C bar, what does that mean? It means if C is a 0, what's C bar? It's equal to 1. That's what we want the output to be. And if C happens to be 1, what's C bar? It's a 0. That's what we want the output to be there. So again, in either case, as long as A is 0 and B is 1, this gives us the correct value for the output. And in practice, it's one of these four combinations. It's either 0, C bar, 1, or C. Let's look at some data sheets. So we've got these data sheets available on the website. Cool. So we've looked at these before, but I want to go through these in a little more detail because you're always going to be dealing with data sheets. Okay, anytime that you start working with a new part, pretty quickly you're going to want to find the data sheet for it. If you buy something from Amazon, some board that you want to plug into something, it never comes with instructions, right? You can find tutorials on YouTube and stuff like that, but if you find the data sheet, right, it'll tell you most of what you need to know. And you get some random board and there's little numbers on the tops of all the chips. You find the biggest chip, you look for the number on top of it, you pull up the data sheet. And there's a good chance that'll tell you how to use this board, at least how to get started with it. In Engineering 270, the data sheet for the PIC processor is about 307 pages. right? You don't print that out, but when I teach it, I usually hand out a short stack of like 20 pages from the data sheet that has sort of the most pertinent information for us. But the whole data sheet is hundreds of pages, but it tells you pretty much everything you need to know about that chip. If you get a slightly different PIC processor, totally different data sheet. All right, so there's like, you know, a gazillion pages on their website. So here's a data sheet for a 2-input NAND gate, right? What could be simpler? So it's got the name of the company, National Semiconductor. It's got that funny looking N next to it. That's a trademark most likely. That's part of their branding, right? It's advertising so that the next time you need to think of a NAND gate, you think National Semiconductor, right? So this is an advertising thing. It's got a date on the top, June 1989. And then right below the company name, there's the part number. So 54LS00, 54, DM54LS00, DM74LS00. And most of these chips, they come in pairs. There's a 54 series and a 74 series. And all of our parts, there's 74LS something, something, something. But there's almost always a 54LS version. So in the 70s, when Texas Instruments came out with their 7400 series chips, and it was the big orange book of part numbers, they introduced 2 lines of chips, 74 and 54. 54 was mil spec. So this was the stuff that the government would buy. It was more expensive, it was higher quality. So mil spec chips could handle more temperature extremes, more vibration. It could tolerate a wider range of input voltages. And the 74 series was the commercial grade, which was less expensive but not quite as durable, right? Not that it would fail more likely, but it was meant to be used in a smaller, more carefully controlled range of conditions. So a 5400 series chip might work if you use it at the Arctic. A 7400 might not. So they have a little blurb here. Alternate military aerospace device 54 is also available. So general description, 4 independent gates, each of which performs a logic NAND function. All right, wiring diagram. So in this case, all of these parts have the same wiring diagram. In some cases, that's not true. In some cases, the 5400 series would have a very different pinout, right? Assignment of pins from the 7400. And the 5400 might be listed first. So if you're trying to hook up a chip, you can't just look at the first picture and use that to make your connections. Make sure that it actually says below 74LS00 right there. All right. Function table, there's a truth table. They do high and low. They tell you H equals high logic level, L equals low logic level. Good annotation of their table. There's the Boolean expression, y equals AB with a bar on top. And then absolute maximum ratings. What's the most that you can push this? So for the 7400 series, the stuff that we have, the supply voltage should be 5 volts. You can go as low as 4.75, as high as 5.25. For the mil spec, you can go down to 4.5 up to 5.5. Wider tolerance for voltages. Logic 1 input level to be high has to be at least 2 volts. It's supposed to be 5, right? 5 is a 1, 0 is a 0. But if you put in 2.5 volts, that's going to be a logic 1. It may be that if you put in 1.5 volts, that could also register as a logic 1. But if it's at least 2 volts or higher, it's guaranteed to be a logic 1. Low input level, maximum value is 0.8. So if you put in 0.4, that's going to be a 0. If you put in 1 volt, don't know. It's higher than the guaranteed 0, but it's lower than the guaranteed 1. So there's a gray zone in voltage levels. Ground will be a 0, 5 volts will be a 1. Bunch of voltages close to 5 will also be a 1. Bunch of voltages close to 0 will be a 0, but there's a band in between that's unknown. And you need to keep your inputs out of that band, otherwise unpredictable behavior. Operating temperature maximum you can put a 7400 at is 70 degrees Celsius. 5400 can go up to 125 Celsius. right? Water boils at 100. So, and it can go down to minus 55. These can go down to 0 Celsius, that's where water freezes. All right, we looked at switching speeds the other day, so switching time for this, somewhere between 4 and 15 nanoseconds for the output to switch from a 0 to a 1 or a 1 to a 0. 5400 a little faster, anywhere from 3 to 10. And then tons of physical data. So this chip comes in a number of different packages. It comes in this form, which is the one that we use, right? So it's a flat pack with 14 pins, and these pins come off at an angle of 95 degrees, plus or minus 5, and the width of each pin is 0.018, plus or minus, etc., etc. All of that physical data is spec'd out on this sheet, right? Why do we care about this? Well, you and I don't. We just take it and we jam it into a board. And if the pin doesn't fit, we bend it, and if it breaks, we get another chip, right? But if you're manufacturing circuit boards, you probably have a machine that's placing these boards into a physical circuit board and soldering them, and that needs to know exactly what's the angle on those legs, because maybe it has to bend the legs to fit into the board. Exactly how far apart are those legs so that it can solder them automatically, right? So all of this is usually automated, and you need all of this information. This also comes in other packages. So this is a flat pack. Doesn't have any pins sticking off the sides. The connections are actually underneath. There's little pads of metal here. And when you put this on a board, it takes up less space, and you don't need to have holes. So you can just mount it on the top. So this is called a surface mount chip. And they're generally smaller, because if you have holes, you've got to have a certain amount of space between those holes. Otherwise, you don't have holes. You just have a big hole. So the surface mount, you can have these wires that are very, very thin and close to each other, and each of these will make a connection to one of those wires. And this is where you get really high density chips. So you might have 100 connections down here, and the whole thing might only be that big. There's more physical. There's another one. This is a flat package. So this one has pins on it, but the pins come straight out on the sides instead of going through a hole. A lot of circuit boards have multiple layers inside. Most circuit boards have multiple layers. Some might have, 10 or 15 layers. And putting a hole through that is really expensive, because it means you can't have anything where that hole is on any of the layers. And if you're going through a hole and you're soldering, you can only connect to the bottom layer. So these flat packages, the pins just come straight out on the side. And it also makes the board flatter because they sit lower on the surface. And then life support policy. So not allowed. You're not supposed to use these chips for life support applications. So that's not going to affect us, because we're not doing any life support systems in our labs. But it's a legal thing, right? A critical component is any component of a life support system whose failure can blah, blah, blah. And you can't use this without written approval from the president of the company. That's just covering themselves legally if their chips are used in some application and the chip fails and it has catastrophic effects. It's saying, we warned you not to do that. And then in tiny little print at the bottom, I don't know if you can read it in the back, basically says we're not responsible for what happens when you use our chips. It actually says National does not assume any responsibility for use of any circuitry described. No circuit patent licenses are implied. National reserves the right at any time without notice to change said circuitry and specifications. So they're not liable for typos either. So that's a data sheet. That's a pretty short one. 6 pages. But every chip has a data sheet, right? And you can find 5 different data sheets for this one part, and they'll look different, but they'll have the same basic information. All right, so that's a NAND gate. Let's look at some other gates. Let's look at the 7447. So this is a chip you're going to use in lab 4. And we started talking about this the other day. So we talked about 7-segment displays, right? These things that look like this. And each of these is an LED, and if you light up the right combination of LEDs, if you light up these 3 LEDs, your display looks like it's saying 7. And so what we would like is some kind of box that takes in a 4-bit number and drives each of these 7 segments, so that if I actually put in the binary equivalent of 7 and I have these 7 outputs connected to my 7 segments of my LED display, if I put in a binary version of 7, it will send a 1 out on the pins that light up those 3 LEDs, and it'll look like a 7. And if I send a binary 0 in, it would light up these 6 LEDs to look like a 0. Not an impossible circuit to design. 4 inputs, 16 rows in the truth table, 7 outputs. So 16 times 7, that's 112 ones and zeros we have to write. And then we have to write 7 equations and cobble that together. And you end up with a big circuit. It looks like this. There's the 7447. So 4 inputs, A, B, C, D, a few other control inputs, and then basically 7 outputs. And it's a glorified sum of products, right? Each of these is a NOR gate, well that's a sum, and each of these AND gates, that's basically doing a product term. It's not impossible to do, but it's a lot of circuitry. So you have in your parts box a 7447, which does all of this for you in one chip. And it's going to make life a whole lot nicer when you're trying to drive the 7-segment display. So let's look at how this works. So 7447, 74LS47 right there. So this is the pinout that we want. And it's slightly different from the 74LS49. For one thing, this only has 14 pins. The 47 has 16 pins. And if all else fails, go to the truth table. That's usually the first place that you want to find information. But there's a picture here showing you what the display will look like for your different inputs. So 0, 1, 2, 3, 4, 5, up through 9. But then 10 through 15 are just these weird symbols from Alien or something. Why? Because we don't have a digit 10. We don't have a digit 11. But they wanted to do something with them. So that's what it displays. If your inputs are 10 through 14, if it's 15, all the LEDs go off. And they have a picture here of a 7-segment display, and they've labeled those 7 LEDs A, B, C, D, E, F, and G. And now here's the truth table. So if your inputs are 0, 0, 0, 0, that's the number 0, your LEDs will be as follow. A through F will be on, G will be off. While A through F, that's those 6 LEDs on the outside, G, the one in the middle, is off. That's your number 0. If you put in the binary number 0, 0, 0, 1, all of your LEDs are off except for B and C. Well, that's these two over here. And if those are on, your display looks like that. It looks like a 1. And so on. So there's some other inputs here, and this is telling us that this LT bar input has to be high. That's a lamp test. If you make it low, all of your lights go on. So you go to a basketball game and they're like firing up the scoreboard, and sometimes it turns on everything. right? You can do that by driving that one input low, LT. And it's there specifically so you can see if all your LEDs are working or if something's burned out. So LT bar wants to go high. RBI looks like it doesn't matter what the value is, but I would make it high for this case. And then these 4 inputs basically affect those 7 outputs. 48 is a different chip, 49 is a different chip. We don't care about that. So really, all we really need from this is the truth table. A lot of this other stuff is about the electrical behavior of it, the operating limits, and so on and so forth. But the truth table tells us what we need to know to hook it up. This one's got an even longer legal notice at the end. So this is Texas Instruments. And so part of working with digital circuitry and digital devices is being able to read data sheets, right? And being able to think about this in terms of its behavior instead of its circuit diagram or its ones and zeros. Logically, what is this doing? Kind of like with a multiplexer. If we look at the truth table for a multiplexer, it's just a bunch of ones and zeros. If we think logically about a multiplexer, it's a steering circuit. It chooses an input to send to the output. And that's often the more useful way to work with this. Well, same thing with this. This is something that takes a 4-bit number and displays it on a 7-segment output. And so in lab 4, you're making your 2-bit adder. Your final answer, which is 3 bits, is going to be displayed on a 7-segment display. And you're just going to feed your output to one of these devices, hook the output up to the 7 pins on a 7-segment display, and it does the rest of it for you. All right, here's a weird chip. This is a 74147. It's called a Priority Encoder. These are all good pieces, good building blocks for computers, by the way. So 74LS147. Sorry, 148. Okay, let's make some sense out of this. So it's got 8 inputs, it's got 3 outputs. We're going to ignore this EI on the left, we're going to ignore GS and EO on the right. I'm just looking at inputs 0 through 7 and outputs A2, A1, A0. And I'm going to draw a picture. First of all, here's the high-level idea of what a priority encoder does. Imagine you have 8 inputs here connected to 8 different kinds of sensors. Okay, this first sensor is saying somebody pressed a key on the keyboard. This next input is saying the time just changed from 8:01 in 5 seconds to 8:01 in 6 seconds, which the computer needs to respond to by updating the time. This 7th one down here might say the CPU is on fire. Okay, it's a much more important event. This 4th one might say we've got a packet of information coming in from the network connector. That's more critical than somebody pressing a key on the keyboard, because by the time the person hits the next key on the keyboard, you're going to have gotten like a lot of data through the network connection. It's a much faster source. So when something arrives on there, you got to deal with it pretty quickly. This line might say the power is failing. Well, power failures are pretty bad, but for a CPU, you can do millions of things before the power actually goes away. Because you unplug a computer, it takes a while for the charges to actually dissipate. And there's enough time to actually do some stuff. So that's going to be a pretty high priority event. But you still want to know about it because you can do things like park the hard drive or save some critical information and so on. So imagine you're a CPU and you're doing your thing, you're playing Pong or whatever it is that your programmer has asked you to do, and something happens, right? The power starts to go out, or the CPU gets really hot, or some information comes in from the keyboard. And you got to stop what you're doing momentarily, deal with that event, and then come back to it, right? And the person who's playing Pong, they're not going to notice anything, because humans, we work really slowly compared to what's going on in the computer. But what event should we pay attention to? Suppose multiple things happen. There's a keyboard press, there's a network packet, and the CPU is getting really hot. Right? Probably we want to respond to the CPU getting really hot first. That's the higher priority event. We want to turn the fan on, make it go a little faster. Right? So the idea is if you have multiple inputs that might require your attention, we can prioritize these and say, let me know what the highest priority event is. So if I have a 1 right here, and here, and zeros everywhere else, I'd like to know priority level 6 is the highest priority that's active right now. And I would like this thing to output the number 6, which would be like a 110. And if this input is a 0, the highest priority input is now input 3. I'd like this to output a 3, which in binary would be 0, 1, 1. And so this is what's called a priority encoder. It basically takes, in this case, 8 inputs, and it tells you what's the priority of the highest numbered input that's active. Okay, you got the idea of the conceptual behavior? So the way it's actually implemented is filled with all kinds of little quirks. So one quirk is that it's not when an input is high, it's when an input is low that it's considered to be active. So in this case, we'd be getting events on lines 0, 1, 4, 5, 6, and 7. Okay, this device assumes that a 1 means nothing is happening, and a 0 means something is happening. So now we've got events happening at priority levels 4, 5, and 7. So it's what we call active low. And this is potentially a can of worms. We always think of 1 as being a thing, right? When something is 1, it's on, it's true, it's happening, right? That's just an arbitrary convention. And we could just as easily say, you know, when this thing has input for me, that data available signal is going to be a 0. And when there's no data, it's going to be a 1. Perfectly fine convention. It's just not what we normally do. But that would be called active low. So a 1 would be off and a 0 would be on, basically. So if all of your inputs are high except for input 2, right, and inputs 1 and 0 don't matter, then input 2 is the highest priority input that's active. Your output should be 2. Well, your output is also backwards. It's outputting a 1, 0, 1, but that's how it indicates that input 2 is the high priority one. So for an output of 2, it's actually not outputting 0, 1, 0, but 1, 0, 1. So if we want to output a 3, we would normally do it like that. But this chip will actually do it with the complement of each bit. That's also part of being active low. 0 means a 1 and 1 means a 0, basically. You can find all kinds of fights online where people either say this is like the greatest thing ever, or people say this is horrible. And it's like a religious war. Pop some popcorn, go to Stack Overflow, and just read up on this. But it's just another convention. All right, so now we can make some sense out of this truth table, perhaps. So if all of the inputs are high, meaning nothing is requesting priority, then the output is HHH, that's basically a 0. If input 7 is low, meaning it's got an event occurring on it, it doesn't matter what's happening on these other inputs, because 7 is the highest priority input, the output's going to be 7, which in this case is low, low, low. If input 7 is not active, but input 6 is, it doesn't matter what happens on the other lower priority inputs, the output's going to say 6, which it says low, low, high, and so on. All the way down to where nothing is requesting, nothing is happening except input 0, and so the output is 0, which is high, high, high. But we don't really need to understand active low, active high, priority encoding, all that kind of stuff. At some level, the truth table tells us everything we need to know. But if we just looked at that truth table, we might have a hard time, unless we've seen it before, knowing why we would want to use this chip. Right? So it's presented as a priority encoder and a description of it, and then we can use this to figure out, okay, so do we need to put the input through inverters or not, and so on. All right, let's look at this one other input, EI. If EI is high, none of these inputs have any effect. X means don't care. That's why I've been writing as dashes. If EI is high, none of these inputs change anything. The output is just high, high, high. That's a 0. All of these things where it's actually doing the job of a priority encoder require EI to be low. So EI, this is what we call an enable input. And a lot of chips have a separate input labeled enable, or EN, or E. And enable basically says the chip is doing its thing or the chip is not doing its thing. And if you don't enable the chip, then the outputs just go into some fixed state and it basically ignores the inputs. And in the case of this chip, the enable input is low when you want it to do its thing, and it's high when you want it to be just kind of like hanging out, and when it's hanging out, it's outputting high, 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 which we treat as a 0. So if you look at a picture of this, a logic diagram, if they have one. So there's the 47. So there's the 7 inputs, or the 8 inputs. There's the 3 outputs. Here's the enable input. And they don't have the pictures that I was hoping for. We'll find another chip. So a lot of times when these things are active low, you see a little circle on the input right next to the chip. We're going to see a lot of that in another week. So we'll dig into that another time. Again, there's a circuit diagram for it, sum of products.
What's the E0 and GS?
Which what?
The remaining 2 outputs.
Oh, so this is an enable output, and I don't know what GS is. Let's look at the truth table. So the enable output, why is that high? Gate select. I'm going to guess here, because I don't play with these, but I'm going to guess that gate select mimics what the enable input is. So you could use that to enable or disable further chips down the line. So you can just drive this one low and the others would get driven low. But I'm not sure what EO is, because it looks like it's almost just a complement, except for that first case. So if all of your inputs are high, meaning none of your inputs are, active, enable output will go low. If you feed that to another priority encoder, that will now pay attention to its inputs. So I think what the purpose of EO is you can have multiple ones of these. One of these chips can only handle 8 inputs. But if you had 16 inputs, you could put another one of these chips below. And you could take EO from that first chip and feed it to EI on the second chip. And if any of these inputs are active on the first chip, EO is going to be high. The second chip's going to be in a state where it's basically outputting 0. But if none of your inputs on the first chip are active, EO will be L, and your second chip will be enabled, and will decode its inputs. So it lets you extend this. And that's a typical application for things where you have both input and output like this. It lets you put them together. Other questions on this? All right, I want to talk about one more device, and then on Thursday we'll start talking about programmable logic. This is where hardware and software meet each other, and it's a fun topic. There's the data sheet for the processor, 310 pages. I was wrong. And I don't see the data sheet here that I want, so we'll just pull it up. This is a chip called the 555, and it's one of the most popular chips ever built. It's one of the best-selling chips ever manufactured. And I need my network connection. I don't have a network connection. So the 555, it's a tiny little chip. It's 8 pins. Okay, if you see it in your parts box, you can tell it right away because it's about half the size of the other chips. And it's called a timer. And it was kind of a skunkworks project by the engineer who built this. He designed circuits, and you could build circuits that would produce pulses at certain intervals or detect when certain things happen in an incoming train of pulses. And it was pretty common practice to build these things, and it would take 3 or 4 or 5 chips. And he had this idea of building a single chip that would do this. And it was just kind of a pet project. He was on sabbatical. He was writing a textbook or a reference book, and he wanted to build this chip. And he took it to the company and said, you know, how about it? Can I spend some time on this? And they said no. And he went to his boss's boss and suggested this, and they were like, yeah, that sounds kind of cool. And so long story short, he ended up producing this chip, and it was like the most fantastically successful product that the company had had up to that point. He said the phone didn't stop ringing for days when they released this. And most of the calls were from engineers just telling this person about something new they had done with this chip. And it was stuff this person had never imagined. It's like the person who made Minecraft, when he started seeing some of the things people were making, it just blew his brain. Same thing, people were coming up with all kinds of crazy applications of this. And there's a lot of cool history around that. One of the warehouses, these chips kept disappearing. And it turned out one of the employees was like taking them home and selling them. Because they couldn't keep them in stock, right? Everybody wanted these. And they eventually figured out who it was. Apparently, as they were taking away in handcuffs, he asked if he was going to get fired. So there's a 555. And there's a block diagram of what it looks like inside. It's made by Signetics, 1972. Right, so you can buy T-shirts with this thing on it. Right? And there's contests held periodically to see who can come up with the coolest circuits using 555s, and people have made. My favorite was an adding machine, and it used old phone dials that you would use to dial in the numbers you wanted to add. And it was just a big collection of these 555s doing the calculations. And So data sheet, so all sorts of stuff inside. These things are transistors, right? We don't deal with those in this course. If you do like 204, 252, 253, the double E sequence, you get into transistors. Mostly transistors and resistors. And not all the pins are used. So some of these pins, they got a control voltage. A lot of times pin 5 isn't even connected to anything. Let me see if they have circuits. There's a nice little circuit. So basically you connect a resistor RA between pins 7 and 8. A second resistor, oh, that's monostable. Second resistor RB between 6 and 7, and a capacitor between 6 and 5. And those are the only components you need, 2 resistors and a capacitor. And if you hook that up, the output bounces back and forth between 0 and 5 volts. It gives you something like a square wave. And you can control the size of this square wave, how long it's high, how long it's low, by adjusting these 2 resistors and this capacitor. And a simple formula is the time that it's on is given by this equation, the time that it's off is given by this. So you can make a square wave, you can make a rectangular wave, you can make a wave that's mostly off but bumps up every now and then. And these things are cheap, right? When they came out, they were, I think they were $1. And the going price was like $5 for chips or something. It was like grossly undercut. And that was part of why they were so popular. But now, you know, it's a few pennies for one of these. So you can set this thing up to just output a train of pulses, fixed frequency, fixed duty cycle, how long it's high versus low. You can build a missing pulse detector. So something that takes an input which should be pulsing at a certain frequency. And if one of these pulses doesn't show up within a certain amount of time, the output of this chip will go high. And so you can put this on an assembly line. You have parts going by on a conveyor belt. You have a light beam. And when the part goes by, it breaks the beam, and you use that to generate a little pulse. And you feed that into this missing pulse detector. And if there's a part that's not on the conveyor belt where it should be, this device will put out a 1, and it lights up a light or sounds an alarm. You go over and you know there's something missing from the conveyor belt right there. Yeah?
So did no one think to make it timer before, or did he just make it simpler and more efficient?
He made it simpler and more efficient, so you could do all these things, but it took 4 or 5 chips. He put it in one chip, right, and it was small, it was 8 pins, and it was really inexpensive. And the timing was just perfect, right, that people just kind of ate this up and came up with all these applications for it. And it's kind of like 3D printing. If you've never heard of 3D printing, you don't wake up in the morning saying, I wish I had a 3D printer, you know. But once you've got one and you use it for things, you know, and it comes to your mind, you can't imagine like not having access to one. So I think it's kind of the same thing. So the 555 you're going to use in one of your last labs to add the yellow light to your traffic light control. Because we can set this up to send out a pulse every 2 seconds, and we're going to use that so that when a car shows up, 2 seconds later the light that was green will turn yellow, 2 seconds later it'll turn red, and the other light will turn green. So we get a nice controlled transition. So we'll use this in lab 6, I believe. All right, so that's plenty of material. Thursday I want to talk about programmable devices, and then we're going to go back, we're going to start looking at glitches, so unexpected behaviors in circuitry, and that's going to lead us into chapter 4 where we're going to start talking about state machines, machines with memory. And I'll post some more homework by Thursday for next week. All right, so I'll see you Thursday.